I'll be talking about the exoplanet aspects of what AXIS can do, but I will actually focus on atmospheric escape from exoplanets. I will touch upon few other aspects of X-ray science that can impact exoplanet research from a very interesting direction, but most of the focus will be on atmospheric escape. So I'm Tansu Daylan. I'm a new assistant professor at Washington University in St. Louis, and I work essentially on atmospheric characterization and discovery of exoplanets. So let's start with some questions. So exoplanet research brings up a lot of very interesting questions. First of all, we would like to understand our solar system, and in order to contextualize our solar system, we need exoplanets because we simply cannot point to particular observables in the solar system and say, you know, we understand this because of the stochasticity. So we need exoplanets to place everything in context. For example, how typical is our home is a great question we ask, the demographic question. Then we ask questions about how planets form. You know, we go from this protoplanetary disk to a well-structured planetary system with a particular architecture. So how do planets evolve, migrate, then potentially lose their atmospheres? And at the end of the day, what makes a planet habitable are the questions we like asking. Now, in this talk, I will mostly focus on evolution, questions that relate to planets evolving, and then also how they lose their atmospheres. For example, on the right-hand side, you see an artistic image of what the Earth could look like losing its atmosphere, or I think you can think of this as Mars kind of, or terraforming at the same time. And on the left-hand side, you see a nice image of our atmosphere. We love our atmosphere, but our atmosphere is susceptible to high-energy radiation. And if things did not go the way they did in the early solar system, we could have lost our atmospheres as well, just like Mars did. So questions like that essentially motivate us to try to understand the high-energy environment of planetary systems, especially early on. Okay, so just for those who don't think about exoplanets every day, I will just do some quick introductions. First of all, there's an accelerated dynamic research field of exoplanets, and we have been discovering many exoplanets in the last 30 years or so. And this has allowed us to identify the diversity of exoplanets in terms of many features they have, which I won't have time to talk about. But as you can see, the number, this is the cumulative number of exoplanet discoveries, and we are just past 5,500 confirmed exoplanets on NASA Exoplanet Archive recently. Now, transits are an important observable, not the only, but one of the primary observables in exoplanet research. So there you basically are looking at a stellar disk, and you have an occulter, and essentially using the physical properties of this system, you can derive a few kind of principal components as your observables: the transit duration and the depth. They allow us to characterize whatever is transiting, both the planetary body itself and also its atmospheric properties. So the transits are, they contain a lot of information. They tell us about the size of the planet. They tell us about how the limb of the star darkens. And they also tell us about the inclination of the transiting object. And using this information, TESS has been conducting a full sky survey, and I have been working in the TESS team. I'm working for the TESS mission for about 5 years since its launch. And with TESS, we basically look at bright stars, and we focus on bright stars because it's a full sky mission. Our pixels are large, but this is nothing necessarily bad. It just means that it's a full sky mission only focusing on bright stars. And with bright stars, we have been doing great stuff. For example, here you're seeing two pie charts, one for the entire exoplanet population, transiting exoplanet population, comparing on the left-hand side the Kepler discoveries versus TESS, and on the right-hand side you have Kepler versus TESS, but only constrained to those with precise masses. So even though TESS is much younger than Kepler, we have been discovering many exoplanets which are amenable to precise mass measurements, hence subsequent detailed characterization. For example, here you see the numbers, the TESS numbers are going up really fast in terms of what we can contribute to the field where we can characterize the atmospheric escape of exoplanets. And here you see the distance distribution from the solar system. Again, this is largely because TESS is a full sky mission looking for bright objects, and that means the host stars are typically more nearby. Okay, some nomenclature for what I will be discussing to make more sense for the non-exoplanet audience, potentially. I just would like to define a few terms here, which I will be using. First of all, let me just go back. This plot shows the orbital period versus planetary radius distribution of confirmed exoplanets. It's color-coded with respect to the detection method. I mean, I've been transits, radial velocity, and others. And radial velocity, radii obviously typically come from just models. So you see some clustering over there. But there are a couple of names we use to refer to these objects. We first use the word giant to refer to anything that's around Jupiter mass. It could be slightly lower mass, higher mass. Then we have these sub-Neptunes. So as a number to keep in mind, Neptune is about 3.8 or roughly 4 times the Earth radius. Earth is down here, 1, and that's Neptune. So between Neptune and Earth, there are two populations that we care about, the super-Earths and sub-Neptunes. So you can wonder, well, super-Earth is larger than Earth and sub-Neptune is smaller than Neptune. So what's really the defining criterion? And that's central to question of atmospheric escape. So I will actually talk about that, but just to give away in a sentence, we think super-Earths are roughly terrestrials, whereas sub-Neptunes are rocky exoplanets with a substantial volatile envelope around them that have not really been evaporated away just yet, or will not. Okay, so if you make a plot this time, instead of orbital periods that was the previous one, instead if you plot planetary radius with respect to irradiation for all confirmed exoplanets, this is the plot you then get. So here you can see the highly irradiated Jupiters, then sub-Jupiters. The sub-Jupiters, they cluster around this area here, which is a few tens of Earth insolation. By the way, this unit is Earth insolation. And just to make sure everyone is on the same page, this is irradiation based on the stellar effective temperature. When I talk to an X-ray audience, we have to probably make this clear that we basically, fit stellar stars with an effective temperature and then extrapolate that to the orbit, semi-major axis of the planet. So this is basically what you get in units of whatever the Earth is receiving at 1 AU from the sun-like star we are around. So basically, this is the picture you'd get. But if you focus to basically between 1 and 4 Earth radius now, this is the picture you get. You still don't see obvious trends. And that's largely because planetary radii are not measured very precisely, especially from Kepler, but also from TESS. It kind of depends on the star's radius and the photometric precision you get. So basically, you have to do some filtering. But before that, let me just highlight that there's an extreme selection bias against planets at low irradiation. So this is basically what we kind of need to keep in mind looking at this plot. So anyways, once you clear out those planets with unreliable or basically very imprecise radii, then this is the plot you get. So going from here to here, basically I just remove those with low radius precision. And then your eyes will probably start to recognize that there's actually a feature here. This basically, this line that exists for only highly irradiated exoplanets, and we call this the radius valley. There's also another feature that you may have just recognized. That's actually the Neptune desert. So those two demographic features are very important. This is just the histogram version, just if you don't like scatter plots. Basically, this is what I'm just drawing with my cursor is the Neptune desert, and then extending into small planets is the radius valley. So we'd like to understand these features. And this is, again, very central and will connect to the X-ray missions. Just to set the stage, as I mentioned, this is known as sometimes the radius gap, which I don't like because it's actually not a gap. It's just a valley. It's, in fact, a very shallow valley. It's not like there's no planet there. But more importantly, it's actually a radius irradiation valley. So it's not just a valley in radius. It's a valley in radius versus in irradiation or insolation. So, and there's actually a slope there, which I will come to why there's a slope, but you should think about this as a valley rather than a gap. And there are various explanations. First, you can just say that this is a relic of planet formation. So if it's gas poor formation, so when the core is forming, if there's no gas around, then you could basically have just some initial distribution that essentially reflected the demographics. And we think that this is unlikely because it actually predicts a slope in the other direction. And then there is photoevaporation. Basically, the idea is that there's high energy X-ray, both X-ray and also extreme UV radiation from the host star, which photoevaporates. And that's basically done first by ionizing and the upper levels of the atmosphere, heating it up, and then that expands and eventually flows outside its throw slope. And then there's a hydrodynamic escape. There's other escapes, like there's gene escape, etc., but those are not efficient enough to carve out the demographic feature that we are looking at. So if it's photoevaporation, then it's likely hydrodynamic escape that's causing this. But then there is also core-powered mass loss, which I really won't talk much about. But basically, the idea is that the energy, instead of coming from the star, comes actually from the internal contraction of the core and the internal energy, essentially, of the planet. But I'll be most focusing on photoevaporation for what's going to follow. So basically, by the way, this is the plot that you get. This is from literature now. This is basically kind of what you get once you undo selection biases. Okay, so let me focus more on the photoevaporation. So photoevaporation, we think, is basically due to X-ray and extreme UV radiation. We call that XUV. As you know, basically this causes low mass planets with hydrogen and helium envelopes to lose their atmospheres through first ionization and then expansion and eventually overflowing their Roche slope, essentially through hydrodynamic escape. And this typically happens in the first roughly 100 million years of the star's life, because that's when the star is mostly chromospherically active, so it's producing most of its X-ray and UV radiation. In the early stages of the life of the stellar life. So essentially, that's when we expect most of the atmospheric escape to happen. So there's evidence for this. This has been shown to exist before. In fact, there's been Lyman alpha absorption measurements, and it's a very tough measurement because you're trying to measure something that's also observed by the ISM. So this is the Lyman alpha absorption by the ISM. So you're measuring the tails, but based on basically whether it's blue or red tail, the wing, you can actually infer that there is hydrodynamic escape and outflow from the planet towards you, typically. And that's basically been observed before. So there's evidence that this is actually happening. Now, I mentioned the EUV. EUV is important, but it's unfortunately absorbed by the ISM very heavily. So typically, it's not available for any star that's further away from about 100 parsecs or so. So basically, X-rays are the observationally accessible handle on this problem that we have kind of in town. So it's our main hope of actually characterizing atmospheric escape. So XUV radiation in general does a few things. It can be grouped under maybe three. Might actually not be exhaustive, but basically I will just list three main aspects. First, it erodes the protoplanetary disk itself, and then it erodes the atmospheric envelope, the volatile envelopes of planets that reshapes the exoplanet demographics that I just showed. And then it also induces photochemical processes in the planetary atmospheres, which I won't talk about. But there's an entire independent aspect of this, which is very important, because if you see photochemical processes like sulfur dioxide, like for example, in a recent study, we used JWST data, for example, to find hints of photochemistry. Those processes are actually induced by XUV radiation too. But coming back to atmospheric loss, atmospheric loss can be characterized essentially in terms of the XUV radiation, that's the insolation, the irradiation in XUV, so energy per time. Then you see an M divided by R cube in the denominator, that's basically the density of the planet. So you can think of this as proportional to the XUV luminosity, inversely proportional to the density of the planet. And obviously you have an A squared, the semi-major squared, so essentially the flux in XUV. This is G is the gravitational constant, and eta is the heating efficiency. So not all of the heat goes on to doing work to expand the atmosphere. Some of it is essentially cooled off, and hot Jupiters are very efficient in cooling off. So typically this eta efficiency is low for them, but it's very high for sub-Neptunes. That's why sub-Neptunes Neptunes and sub-Neptunes lose their atmosphere very efficiently, and they're subject to atmospheric loss through this photoevaporation process. This eta you can think of is actually a function of it's a power law in the escape velocity, which obviously is inversely related to that. So as a reminder, planets' densities depend on their mass. First, they grow because they're terrestrial. They basically squeeze, they become denser, and then they pick up volatile envelopes, and suddenly their density starts dropping. So these are the Neptunians, and then Jovians again, they start gathering more and more gas, and they start to contract, and that contraction causes the densities to go up again. So you should keep in mind this density evolution. So similar here, just bend in mass. One thing we already see in this population is that if you just look at the yellow points here, the yellow points, which is the lowest mass spin here, irradiation again versus planetary radius, we think that lowest mass planets are highly inflated, and this inflation is a precursor to atmospheric escape. They get inflated, and if they get enough inflation, then they will start undergoing atmospheric escape. So given this, just going back to the plot of planetary radius versus irradiation and the radius gap, the planets in the Neptune deserts most efficiently go down, and very fast, within just a few million years when the planetary system forms, whereas those on the far left, like for example 10 to 100 irradiation, Earth irradiation, there only the planets with the smallest cores can undergo planetary atmospheric loss. So because of that, the gap, the line that separates the sub-Neptunes from super-Earths actually go down. There's a positive slope in irradiation, or equivalent a negative slope in orbital period. That's why we have a slope here. So it's the lowest cores that can only do that at low irradiation. So As I mentioned, just looking back here, there's the XUV here in the numerator. So we need those XUV fluxes, and they so far have come from Rosat mostly. There's also XMM, Newton, and Chandra data that allow us to characterize these exoplanet hosts, but only about 300, fewer than 300 planets, or planet hosting stars, I should say, have been characterized in X-rays so far. And we need many more of them in order to actually solve this puzzle as a function of stellar type, stellar age, etc. So this is basically a line that's expected from E Rosetta, and this line at about -16 ergs per centimeter square per second is basically is the expectation from AXIS given its high effective area and high angular resolution, 20 kiloseconds, so about 5 hours of exposure would get us down to about -16 on this plot, and that's very crucial because if you integrate the total number of stars, planet hosting stars, to the right of this line, you get about 2,000, just below 2,000. So that would definitely increase our ability, maybe 1,500 or so actually. That would definitely boost our ability to characterize the exoplanet population and its demographic features. So maybe I should speed up. I think I have like 5 minutes left. So how do we make progress? Well, first we need, again, these XUV radiations and also XUV radiation and also its activity level, not just the baseline, but the activity level. This is from literature, a recent paper that actually modeled the X-ray luminosity as a function of system age. You can see it running, and this is basically kind of the observational constraints, the red ones that are measured. But we need this over a much larger sample set, and we also need the activity levels. And on top of that, we also need systems where we can actually test this. So I will just very briefly talk about that in order to test photoevaporation models, we need comparative atmospheric characterization. By that, I mean systems where there's multiple planets that are amenable to atmospheric characterization. TESS has made significant contribution to that. So this is basically TESS discoveries in blue and Kepler discoveries in red with precise masses. Again, for small planets, we are adding a lot to the picture. And one of the highlights from TESS mission was TOI 1233 that I want to highlight here, which is basically a planetary system with 5 planets. I led the discovery of 4, and then Cheops discovered the 5th one. So TOI 1233 is the brightest sun-like star to host at least 5 transiting exoplanets. It's an outlier in this plane here. So if you look at that in this plane, I just drew, basically it spans both sides of the radius valley, and that's very exciting because we can actually use systems like these, whereas, I mean, TOI 1233 is a highlight system, but there are few of them. So we can use these to test photoevaporation model. Let me just skip these because I don't have time. I just want to get to the end and cover a few other things. So basically the message I want to give is we need the XUV luminosity as a function of stellar mass, age, and also rotation periods. So this is irradiation, again, based on stellar effective temperature versus age of the star. We need this essentially in X-rays. And we similarly have demographic properties, for example, of the current exoplanet population in terms of their system age or in terms of their stellar mass, host mass, but being able to add to these the X-ray luminosity dimension can allow us to figure out more demographic properties of exoplanets. One other thing that AXIS can actually do is go spectral and actually find activity indicators that can tell us the activity level of the chromosphere. And again, this is an orthogonal measurement to just the baseline XUV radiation, and that can allow us to understand some of the anomalous features of the demographics, because, for example, sometimes we see planets in the Neptune desert. So normally you wouldn't expect those, and in fact they're sometimes not even very young. So you might ask, well, it's not very young, so why is it not? Why is it in the Neptune desert? There might be anomalously low activity stars, and we can actually start characterizing them with AXIS, with the spectral resolution it has and the effective area. So I made a list of what AXIS could do, and this is like a long list. I may not have time to go through it now, but basically we have there are a couple of things I can highlight. AXIS has a really high angular resolution, so it will actually decrease the dilution in transit characterization. So we will actually decrease the error bars on the radius measurements once the transits are measured or observed. It can also look for transiting planets around X-ray binaries. We also had one example of that recently. It can look for stellar flares, and that actually helps characterizing habitability as well. It can improve the stellar activity modeling. And for example, when JWST tries to do transmission or emission spectroscopy, we fight against stellar variability. Actually, stars are very variable in X-rays and EUV, so characterizing that variability is very critical. AXIS can also target many of the faint stars that we have, faint but M-dwarfs, so very particularly suitable for X-ray studies. It can target one of the many of the faint stars that we have been recently focusing on using the TESS mission. It can target the young planet hosting stars that TESS has been finding. On the right, you see the young stars, the distribution of the stellar age that TESS has been discovering, and these are really young systems. AXIS can also look for transiting planets around white dwarfs, and that's a very compelling science case. Ties back to both biosignature searches as well as planet formation model testing, because we would like to understand how these planets can actually form or rather migrate afterwards. Let me just skip this. The last thing I actually want to talk about is stellar flares. We know that X-rays are, EUV and X-rays are great for studying stellar flares. And they can actually tell us something about the habitability prospects of planets around these stars. In general, habitability requires some stellar flares to happen, but it requires them to be rare, high amplitude, but rare, so that it doesn't disrupt the arrow of biological evolution. So one of the recent work that I have started at WashU with my graduate student Nathan is looking for induced stellar flares. This is not necessarily directly related to habitability, but rather to planets crossing the Alpine surface periodically, and this can actually allow us to search for star-planet interactions and actually characterize atmospheric loss as well as the planetary magnetospheres. It's a probe of the planetary magnetosphere, and again, AXIS can contribute to such studies because it has a really high contrast ratio as well as depth to do this science. So this is my conclusion slide. I will leave it up and just take any questions. Thank you.
Okay, great. Thanks, Tansu. Do we have any questions that people want to ask? So I'll ask this question, basically, what do you expect the landscape will be, when these probe missions launch 10 years from now? And how will like an X-ray mission like AXIS sort of fit into the much larger number of exoplanets will have, the years of taking, JWST data on some of these systems. Like, how do you think about that?
Okay, so there are a couple of, again, directions that are all independent. I think, by the next decade, we should have few planets around white dwarfs and many planets around the radius valley that are all amenable to atmospheric characterization. So AXIS will have a really rich target list to do pointed measurements, maybe like potentially deep measurements. We're talking, plus 100K seconds measurements of particular targets like TRAPPIST-1 and some of the targets I mentioned, like the young systems. So I think those will be prime opportunities to answer some of the fundamental questions we have. For example, one of the compelling questions is whether photoevaporation is actually the right answer. I did not talk about it a lot, but core-powered mass loss can also explain some of this. So in order to test photoevaporation model, we definitely need access-like data on some of the systems that are prime targets for comparative atmospheric characterization. So there are compelling science questions that very, very specific questions that an access-like mission can certainly address. On the side of planetary habitability, again, there's going to be interesting progress, because as we find more planets around white dwarfs, they will be subject to biosignature searches directly by JWST. I'm not talking about ultra cool dwarfs like TRAPPIST. I'm talking about Earth-like planets around white dwarfs, and there we access. I mean, white dwarfs are really hot systems, so they can access like missions can definitely characterize them. So I think they'll be the prime science cases for exoplanet search and characterization.
Okay, great. So if people have additional questions, let's put them in the chat.